Hello, welcome everybody. We are in our second installment here, our second video for this course, and we're going to be looking at this inquiry activity that is entitled Organizing Data. We're going to continue our kind of theme of talking about experiments and labs. Anytime that you have data collected, you want to be able to organize it in a very clear and concise manner so that it is easily interpreted and easily analyzed. If you remember from the last inquiry activity, we talked about experimental data, and we talked about designing an experiment. We talked about different variables: controlled variable, independent variable, dependent variable, and just setting up a good design for your lab, for your experiment, so that you can glean information from it and make it useful. So we're going to continue that and talk a little bit about what do you do with that data? How can you best organize it, in what different formats, maybe a table or a graph, and how is it best useful? Okay. So scientists rely on data, numbers, quantities that are collected during an experiment to describe nature and uncover relationships. So this is really key here. We're going to be looking at relationships. That's really what we want to find out in many cases, is when something increases, what happens to something else? When something decreases, what happens to something else? Okay? The raw data, meaning the measurements, the values, the quantities that you take and record from your lab are useful if you organize them, or I should say when you organize them, because you're going to want to organize them in a particular fashion. By organizing them, we make those relationships a little more clear. Okay? So in this activity and in this video, we're going to talk about two ways that we are going to organize data. And again, the reason is it helps us to analyze that data. Here in Model 1, we are given information, data that involves copper samples. So you'll notice here we've got 7 different groups. We have a volume, we have a mass, we have a substance. In all cases it is copper. Okay? The units here are given to you in parentheses right after the heading title, so you know what is being measured and in what units. On the side here, we are told that the room temperature is 21.7 degrees Celsius. It doesn't look like that's changing, so that is a constant in all cases, in all of these different samples. So let's start with the questions. They're going to start pretty basic, and we'll look at the conclusions and observations and the analysis of all of this as we move forward. Number 1 says, what substance were the students working with to obtain the data in Model 1? Well, that should be obvious here. Simple question, simple answer, that would be copper. Number 2, what variables did the students measure to produce the data in Model 1? So your variables are, you've got the volume, you've got the mass in grams, and those two things are measured. Those are the ones that are changing. You'll notice those values are changing. The room temperature was also measured, but it is not changing. It is constant. So volume and mass and temperature. Number 3, briefly describe an experiment that the class might have done on that day that the data in Model 1 was collected. Discuss your answer with your group members to be sure there's consensus. Well, you may not have group members there, but we can talk about it here, and if you do have somebody there that you can discuss it with, you can do that. But basically, you're looking at this and you're saying, okay, well, they are looking at volume and mass and different samples of copper at the same temperature. So in this case, maybe each group was given, these are different groups here, each group was given a different sample of copper, sample of that metal, and they were required then to mass that sample and find the volume of that sample. So they're looking really at what's the relationship between the mass and the volume. So they're looking at volume versus mass. Number 4 says, consider the data in Model 1. Again, which variable was the independent variable in the experiment, and why do you think it was the independent variable? So the independent variable, remember, that is the one that you choose to change. You get to change that, and that is up to you. Okay? So probably my guess would be that the instructor gave every group a different sample of copper, and those were different sizes. So probably volume is going to be independent variable. Okay, the instructor just grabbed different size samples of copper. Doesn't know what the mass is yet. The instructor didn't mass them before maybe giving them to the groups of students. So in this case, your independent variable would be volume. And then the variable here that is the dependent one, in other words, the one that changes as a result of the volume, would be your mass. So this one, the independent variable volume, that is the one that is determined by you. You're going to grab different sizes of the sample of copper, and then you're going to mass that. Okay, this is something that you do. You would actually, this is your action. This is your action that you do. You mass it, and from these different sizes of copper, you would then determine what the masses are. And these masses are going to be dependent on what the volume is, or the size of the copper. Okay? Two controlled variables. Well, if we look back up here, the controlled variable, one is the type of metal and also the temperature. So those would be your two controls. Okay, type of metal and the temperature. How is the data organized? Well, if we look here, the data is organized in a table. You have headings, you have different columns, and that is allowing you to look very quickly and easily at the information and gather information from it. But in particular, what you need to know, it is in an order by group number: 1, 2, 3, 4, 5, 6, 7. It's not in any particular order when it comes to volume and mass. So the group number is probably just arbitrarily assigned to a group of students. But you'll see the volume goes from 2 to 6 to 10 to 8, 14, back to 4, up to 12. It doesn't look like there's a pattern there. Same thing with mass. So this is organized by group number, which may not be the best way to organize this in order to try to draw some type of conclusion or see some relationship. Okay? Alright, and then it says, is the table in Model 1 organized in a way that helps determine the relationship between independent and dependent variables in the experiment? And I would say no, it's not. The independent variable and the dependent variable are not in any particular order. So the independent variable is not in a particular order. So it's not very helpful, the way that it's organized. So what would be a better way? Propose a better way to organize the data in Model 1. And then we can fill in the data here. Well, maybe since the independent variable is volume, maybe we organize the volume in an ascending order, in increasing order. So you might put the values here as they are increasing. And now we begin to see, oh, I see what's going on here. There's absolutely a pattern. What the instructor did is gave each group member a different volume of copper, and it increases by 2. So 2 cubic centimeters, 4, 6, 8, 10, 12, 14. And then we're going to write down the accompanying mass that goes with that volume. So this one had a mass of 17.92, this one 39.80, 50.89, 79.30, 93.45, we had 103.85, and 125.44. And all of these are copper. All of these are copper, copper, copper. Okay? But now the group numbers, notice, are not going to be in a particular order, and we don't really care about that. But this would be group 1, this was group 6, this is 2, this is 4, this is 3, and this is 7, and we have 5 here. But this is really what we're interested in, putting the volume in a particular order and seeing how mass changes as a result of that. The data table in question 6 should allow you to state a relationship between the variables involved in the class's experiment. So complete the following statement. Now we see here, if you look, now we can see as volume increases, yes, mass is going to increase. We can make a statement just that simple right now, just by looking at the data the way it is organized now. As the volume of copper increases, the mass of copper increases as well. Okay, we don't have a particular formula right now, but we're just looking at, is it a direct relationship? As one increases, does the other increase? Or is it an indirect relationship? As one increases, the other decreases. When scientists design an experiment, they are usually looking for a cause and effect. In other words, one changes, the other changes in one manner or another, between the independent variable and the dependent variable. So organizing the data by the independent variable is the easiest way to reveal that relationship. When the data is not organized that way, the relationships are not very evident. They're hard to find. Here in Model 2, you'll notice what we have. We have some graphs given to us. And these are different types of graphs. We're going to talk about these graphs and how we set them up, how we organize them, what we can get from them, and why they are very, very helpful. Number 8. Identify each of the graphs in Model 2 as a bar graph or a scatter plot. So in this case, a bar graph, hopefully you know this already, it's really by the name it kind of gives it away, but you will see that the bar graph is graph B, and the scatter plots are the other two, and that would be A and C. Okay? So bar graph, obviously we have bars here. Scatter plot are the points that are on the graphs for you to recognize which is which. Number 9, one of the data points in graph B indicates that a volume of 8 cubic centimeters has a mass of 80 grams. Which other graph in Model 2 shows this same data? So let's look here. We have, let me read this again. In graph B, volume of 8 cubic centimeters has a mass of 80. So 8 goes to 80. Let's see here. You can see along the bottom on the x-axis we have volume in cubic centimeters increasing from 0 up past maybe around 12 here. And notice though that this is not really put in any particular order. It's 2, 6, 10, 8, 14, 4, 12. This is, I believe, according to how the Model 1 data was originally given to us. So 8 cubic centimeters, and the bar goes up to 80 grams. So the other one that shows that, well, let's see here. We got to find 8, 4, 8. Here's 8. There's nothing for 8 on this one. If I go up to 8, there's no point on this line. But if I go to graph C and I go to 8 and I go up on 8 and there's a point there, and I go over to the y-axis, and it is indeed 80 grams as well. So graph C is showing that 8 cubic centimeters has a mass of 80. Okay, so that would be graph C. Of the 3 graphs in Model 2, which illustrates the relationship between the variables that you stated in question 7 most clearly? So if we look back at question 7, we're looking at this relationship here. Remember, as the volume of the copper increases, the mass of the copper increases. So we're looking for that relationship. If you just look at the graph itself, hopefully it is very evident. Even though these are increasing, this is group number, and this is mass. So we're not really looking for a relationship between group number and mass, and it doesn't appear to really be an obvious one. It goes up, it goes down, up, down, up. There's not an obvious relationship between group number and mass, and there shouldn't be. Here, this is organized by volume and mass, but it's not in ascending order, meaning the volume is not put in ascending order. So it's hard to see whether there's a relationship between volume and mass. Goes up, goes down, goes up, goes down, goes up. Here, this one is organized such that the volume on the x-axis is put in ascending order, and when we plot the volume with the corresponding mass that goes with it, we see that indeed these values, these points are going up. Not necessarily all on the same line, but the trend, the tendency is an increase in the mass as the volume increases. And you can see that just by kind of eyeballing maybe a line that might fit best to all of these points. If you were to take a straight edge and not necessarily connect all the points, but just draw a line that best represents that trend that is occurring with these values. You draw a straight line maybe where you kind of put half of the points above the line, half below, and you might get a nice straight line that looks maybe not quite like that. I should have gone up a little bit more maybe. But you can see there is an increase. As volume increases, mass increases. This would be your direct relationship between volume and mass. Okay? So again, graph C is showing us that that relationship very clearly because of the way it was organized. You get to choose how to organize it. So hopefully you'll choose a graph, in this case graph C, that clearly organizes the data so that we can draw some conclusions from it. Model 3, more examples of graphs. We've got a graph D, a graph E, and in this case, let's just pause for a second and let's look at these and analyze these and see how they are set up, and maybe you can see how one maybe is good or maybe it's bad or maybe it's not very helpful. But in any case, this one, the title is always important, chocolate candy colors, and we've got the different colors here. And then the bar graph is very probably useful and helpful in this case, and this is the average number of candies in the bag that are this color. So the bar is going to go up to a certain value that is indicating the average number of candies in that bag of that color. Over here we've got leg length and then sprint time. So maybe this is the measurement of somebody's leg, how long is their leg, and then how fast can they run a certain distance in a certain time in seconds. So leg length versus sprint time. And again, this is organized where the leg length increases and the sprint time is going up this way, and we're going to see, is there any correlation, is there any connection between those two. Okay, so they've organized these graphs very well. Alright, number 11, identify the independent variable and dependent variable for each of the graphs in Model 3. So let's just identify. So if you're given a graph, you should be able to indicate and quickly determine which is the independent variable and which is the dependent variable. So in this case, you've got in graph D, your colors here, the candy color, is going to be your independent variable. And for the other graph, graph E, that would be the length of the people or the person's leg. Okay? Dependent variable. Well, the dependent variable is the other one that's along the x-axis. That's one that's changing when you change the independent variable. And in this case, for graph D, that is the number of candies of that color. Okay? Number of that color in the bag. Over here, it is the sprint time along the x-axis. Match the experimental questions below to the appropriate graph for Model 3. Remember we talked in the last video, we talked about how the design of the experiment really should be such that you are answering a question. So this graph should help us answer a question. When you set up data in a useful, organized manner, you should be able to answer the question quickly. Match the experimental question. So A says, is the number of candies in a bag of chocolates dependent on the color of the candy? hopefully you see it's obvious that that would be graph D because it's talking about candies and colors. And then the other one, length of a person's leg, affect the time in which it takes them to sprint 60 yards, and that would be graph E. So these questions are going to be answered as we look at the graphs above. Number 13, why was the data for graph D plotted in a bar graph? Well, in this case, the independent variable really is it's not a quantity, it's not a numerical quantity. It's just colors. So there's no way to really organize the colors in an ascending or increasing or decreasing order. So you just list the colors in any order you want to. So we're not looking for necessarily a relationship between the increasing of the independent variable, because there is no increasing per se, and the increasing of the dependent variable. So you could just list these in any order you want to, and a bar graph is very helpful in that case. Okay, so this is, we just say non-numeric. All right, the independent variable here is non-numeric. And 14, using the graphs in Model 2 and 3 as examples of proper graphs, identify the axis X or Y where you would usually plot the independent variable. Hey, we already talked about that. So the independent variable always goes on the x-axis, okay? This is your x-axis. This is your y-axis, okay? This is your x-axis. This is your y-axis, okay? All right, so independent variable is on your x-axis. And therefore, it stands to reason that your dependent variable would be on the y-axis. Okay? All right, let's go on here and let's look at question 15 on the next page. It says, for each of the following experiments, choose scatter plot or bar graph as the most appropriate way to display the data. Justify your answer. So here we have A, students heated oil on a hot plate at the number 4 setting. That means the number 4 setting on the hot plate. You just turn it to 4 on the dial for different amounts of time. They wanted to answer the question, how long do you need to heat an oil bath to reach a given temperature? Notice this is your variable that is not changing, so I guess it's not really a variable, but this is a constant volume. You don't want to change that. The hot plate setting is always at 4, and the initial temp is the same all the way through, because all you want to determine is there a relationship between these two variables, time of heating and the final temperature of the oil. Well, hopefully there is an obvious conclusion here. Okay? And the nice thing is that they have organized this by your independent variable increasing from 0 to 20 in increments of 5, and you're able then to see what the effect is on the dependent variable. So in this case, for A, you probably would want to use a scatter plot. Okay? The other reason is because, the reason you want to use a scatter plot is because you didn't heat this for 2 minutes, or for 8 minutes, or for 13 minutes, but if you do a scatter plot and you draw a trend line, you could estimate what the time of 8 minutes would produce, what temperature that would produce, okay, just by looking at what's called the trend line. So you don't need to do every single possible time, you just do a selection of time, in this case 0, 5, 10, 15, 20, and then when you draw your trend line, again, it's not connecting the points. If you look up here, you don't connect the dots when you draw a trend line. You don't do this. All right? You draw a trend line, and this is really not much of a correlation here, but you draw a trend line that best represents the trend that you observe in this situation. These two here are way off of the trend line tendency, but in any case, you could then, even though you didn't collect 90 a person at a leg length of 90, you could estimate what would be their sprint time if somebody has a leg length of 90. That's the power of a trend line. So this would be using a scatter plot, and it helps you to estimate the temperatures of times that were not recorded. B, let's look at B. In this case, you've got students measure the height of each person in class. They wanted to answer the question, what is the most common height among 10th grade students? So, under 4 foot, 1. Between 4'1" and 4'6", 3. Between 4'7" and 5, 5. Between 5'1" and 5'6", you got 9 students. Between 5'7" and 6 foot, you got 3. And over 6, you've got 1. This would best be a bar graph. Okay? Because you've got groups here, you got categories. Category 1, and you put a bar that goes up 1 unit. Category number 2, etc., etc. Okay? C, it says we've got different types of salmon and the average weight of those. Again, you'll notice here that your independent variable is non-numeric, so you're going to want to use a bar graph in order to organize this. Okay? The bar graphs are equally as powerful as a scatter plot, because you could quickly and easily, by comparing the heights of the bars, see which of these salmon species has the highest average weight. Okay? You don't have to look through all these numbers and scan. You can just easily pick it out because it's easy to visualize. D, we have here the National Oceanic and Atmospheric Administration measure the pressure of the atmosphere at various altitudes. So you've got altitude, atmospheric pressure, altitude, atmospheric pressure. This just continues, by the way. This column then continues right here. Okay? And you'll notice that the altitude would be your independent variable, and it is increasing as we move down that column. And then the atmospheric pressure would be your dependent variable, and it is changing as the independent variable is altered. It's going down quite dramatically. Okay? This one would best be graphed using a scatter plot. And you would put the altitude on your x-axis, increasing, and then your y-axis, you would plot the points here, because on your y-axis you would have the pressure. Okay? And you'd be able to see the trend. You'd be able to see that as altitude increases, the pressure is going to go down. So it's going to be it's going to be a indirect relationship. One goes up, as the altitude goes up, the pressure is going to go down, and your graph is going to look like this. Your trend line, I should say, is going to look like that. You're going to have points that trend or tend to decrease as the altitude is increasing. Number 16, choose one of the data sets in question 15 that you selected as appropriate for a scatter plot and graph it here. So, in order to do that, again, you can choose whatever you want. I'm not going to do that, but I'm just going to make a few comments. Let's say, for example, we did the well, let's do the atmospheric pressure one, because that one is an indirect relationship, one that we haven't seen a scatter plot for. So along your x-axis, you would put the atmospheric pressure, and don't forget the units. So you would have your units here in ATM, which is a measure of pressure. You would also have a title, so you can choose the title, but make it descriptive, make it helpful to the reader so they know what it's about. So you could just have atmospheric pressure here. You could say, altitude versus atmospheric pressure, something like that. On your x-axis, you're going to have the altitude, and make sure you have the units there in meters. And then you're going to choose how to write down the values. So you want to look at your values on your atmospheric pressure and notice that they go from 0 all the way up to 48,000, over 48,000. So you want to divide your x-axis here in a way so that you can accommodate all those values. So maybe you want to count by 10,000s or by something like that. So maybe this is 0. And then 1, 2, 3, 4, 5. Let's say this is 10,000 here. 1, 2, 3, 4, 5. That's 20,000. 1, 2, 3, 4, 5. I'm not even going to make it fit on here very well. Let's see. 2, 3, 4, 5. Yep, 30,000. Okay. So I didn't make it fit very well. You're going to do a better job than I did. You might want to count every 2 is 10,000. That would make it fit better, because I'm not going to have room to get up to 48,000. And then the atmospheric pressure, you restart the plot here. So the atmospheric pressure, you notice, will go from 1 down to 0.001. So my 1 is my highest value, and then close to 0 is my lowest value. So I'm going to choose here. We've got, let's divide this. This is going to be 1, 2, 3, 4, 5. That's going to be 0.5. 1, 2, 3, 4, 5. That's 1. 1, 2, 3, 4, 5. 1.5. Okay? So you will then plot these values, and at 0 it's 1. And then continue to plot these pairs of values: 2750, 0.75, etc., 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 etc. And you should see a graph that has the points descending, and then it's going to kind of level off as you get higher and higher. Okay? In this case, a trend line, a linear trend line, may not be the best. This would be more of a curve, a trend line that would be more of a curve to it. But we don't have to worry about coming up with a formula at this point. Alright? And then here it says do one with the bar graph, and again you want to label it. So maybe you say student height. And you're going to put your different categories down here. So for example, under 4 foot here, this is going to be between 4'1" and 4'6", and then you make the other categories here, and then along the y-axis you've got your different number of students. So 0, 2, 4, 6, 8, 10, and for under 4 foot there's only 1, so this bar here is going to go up to just 1. Between 4'1" and 4'6" there were 3, so that's going to go up to 3. Shade that in, and you get the idea. So for each category you're going to draw your bar up to the appropriate number. Okay? Alright, number 18 we don't need to talk about because we don't necessarily have groups, but if you are working in an environment where you do have a group, you can talk about this in your groups and share your graphs and talk about them and see how everybody did. Okay? So hopefully this was helpful as we talk about these inquiry activities, and in particular where you're talking about setting up labs, organizing data, and making it so that it's useful. That's really the point here, is you want to organize all of this so that it is helpful to analyze and critique and draw conclusions and see relationships. Okay, let's look at the extension question at the end of this inquiry activity, Model 4. And I'm just going to move quickly through this because it's trying to make a point, and I can get you to that point fairly quickly. Model 4, we're looking at SAT scores, Graph F and Graph G. We're just going to compare the two. You'll notice the data is it's the same values. We're looking at a particular college, college A, B, C, or D, and the SAT scores of the students that are entering that college, the average SAT of incoming freshmen. Same colleges, A, B, C, and D over here in Graph G. Same title, same y-axis, same information on the x-axis. What is the only difference here? And this is why you need to be careful when you're interpreting data from graphs. The difference is along the y-axis over here, they're starting at 0 and going up to 2,500. And in graph G, they're starting at 1600. So they basically have chopped off, right here, if this is about 1600, they've chopped off everything below 1600. That's all gone. And they're showing just this portion of the bar graph. And they have extended it the same, it's kind of the same height as graph F, and they're going from 1600 up to 2400, 2500, but it has to be stretched out more because the values, the increments are smaller. Here every increment is 500. They're counting by 500s. Here we're counting by 100. So as you look through this extension question, the point of this extension question is conclusions may be drawn from looking at a graph, but those conclusions may be inaccurate, and you might want to look back at the actual values and the data. So you have independent variable. Here is the type of college, or the college name. We don't know what name it is, but A, B, C, or D. And the SAT score, the incoming freshman, that is your dependent variable. Okay, so that's 19. When you look at the graph F, what message is communicated by the relative lengths of the bars to prospective students about college D's average SAT scores compared to the other schools? So graph F, D here, obviously D is higher than all the others. Okay, it's simple. It's just a simple question. It's just saying that college D has an average SAT score higher than all the other colleges that have been compared to. Again, graph G, what message is communicated to the relative lengths of the bars to prospective students about college D's average SAT scores compared to the other? Look at how much higher it appears that college D's SAT scores are compared to the other colleges. Okay, if you don't look at the numbers and you don't analyze this correctly, it's going to appear as if D is so much higher than A, B, and C, whereas in reality it's really not that much of a difference. And so that's the point of this extension activity, is to be careful looking at data. You also want to look at the values of those of that information. Okay. For each of the graphs in Model 4, estimate the average score for each college represented by the height of the bar. Is the data being displayed in the two graphs the same or different? The values are exactly the same. So this one here is about 1700, that's about 1700. This is about 1900, that's about 1900. The values are exactly the same. Again, it's just the way that it's being represented, that over here in graph G, it appears as if this column D is so much taller than the other ones, because the graph, the y-axis on this graph has been stretched out. So that's the point. A student takes a quick look at graph G and says, based on the size of these bars, it looks to me as though college D had entering freshmen with SAT scores nearly 4 times higher than college A. Explain to the student what mistake he has made in processing information. So again, he's not looking at the values. He's just looking at the way that this graph has been represented, with lots of the bar being chopped off. He's not looking at the actual values. But if he just looks at the bar height, yes, it appears as if, man, this bar over here, D, is probably 4 times higher than bar A. But in reality, if you look at the numbers, and that's why you should also have a data table with the actual values, the numbers there, that is not the case. Okay? All right, I hope that's helpful, and I hope you do these extension questions. They are meant and designed to kind of take you a little bit further, a little bit beyond just the basic information and the inquiry activities. All right, thank you very much, and we'll see you in the next video.